Hi everyone, so this is question 4. So let's take a look at the question first. So it mentions here that you are given a displacement against distance graph. Displacement against distance, or in short we call it displacement distance graph. Okay, displacement distance graph. Okay, it's important for you to know what graph are you given or what graph do you need to draw, because there's two types of graph in chapter 10. One of it, we call it the displacement distance graph, which is a y-axis graph, and there's another one which we call it displacement against time graph, which is y against t. So it's important to know what you need to draw or what you are given in a situation. Okay, so after time t, after time t here means by it's a specific moment which is t seconds or t minutes since the start of the time. Okay, after time t. Okay, for the progressive wave, again is a progressive wave which propagates to the right with a speed of 50 cm per second. If it's 50 cm per second to the right, we are not sure how we are going to use this. We can just label it maybe something like this: v equals to 50 cm per second. Okay, it's good that we extract the information first. Okay, so that's all that is given in the statement. Before I move on to the question, as usual, I will usually prefer that we unpack the diagram that's being given to us, extract all the information that we have. Only we start to see what is the question asking for. So over here, it's a little bit different from SHM graph, so you have to be really careful of what you are extracting. Okay, the first thing that you may extract is this. For this, it is still similar to your SHM graph. Okay, it's still the same old amplitude, so the amplitude here is still 3 cm. Then the next thing that we can know, which is slightly different from chapter 9, is this thing over here. Okay, because it's a distance on the x-axis, that means that one complete oscillation, this double-headed arrow here, represents the distance covered by one complete oscillation. If it's the distance covered by one complete oscillation, I believe you know this is just representing the wavelength of the wave. Okay, this is the wavelength of the wave, and you can see it's equal to 1.0 cm. And this wave is moving with a velocity of 50 centimeter per second. Okay, that's the important things that we can extract from this displacement distance graph. You can think of a displacement distance graph as like taking a snapshot or taking a picture of a wave. Okay, so this picture here, this sinusoidal wave here that you see here, is a specific moment of time. It's the shape of the wave at a specific moment of time. Okay, at different distance, it has different displacement from the equilibrium. You can think of this as taking a picture of the wave. So this represents the shape of the wave at a specific moment of time. So the time here is fixed. That's why they say after time t. Okay, later we'll move on to talk about displacement, the difference between displacement distance graph and displacement time graph in the next question probably. Okay, so after extracting all the information, it's time for us to solve the question. The first question asks for the wave number. So if you have been following me since question 1, you know wave number is related to wavelength. Okay, related to wavelength using this formula. K equals to 2 pi over lambda. So now it's just a matter of substitution. 1.0, then you will end up with 2 pi per cm. Okay, be careful with the unit, it's not SI here. Okay, it's not B here. Okay, so the next thing they ask for is the frequency of the wave. So you have lambda, you need frequency, and you have velocity. Well, probably something from SPM knowledge, probably just ring the bell. V equals to F lambda. Now it's a matter of substituting 50. Then F is what you are finding. And then your lambda is 1.0 cm. So if you shift around everything, your frequency will just be equals to 50 Hertz. Okay, very direct question. Let's move on to question B. So the question B asks for an expression. They want us to write an expression expressing displacement as a function of x and t. Okay, so we want an expression for displacement, and displacement we know that is just y. Okay, then this y have to be a function of x and t. Well, does it ring any bell for you for now? If no, well, you have encountered it in the last question actually. So if you look over here, this is a progressive wave equation. Progressive wave equation here, you have an expression which is y, and it's expressed in terms of t and x. So this y here is a function of t and x. And in question 4b, we are also asking for an expression for displacement as a function of x and t. So well, actually we are looking for something like this. So we want to look for something like this. Probably we need to get this, copy this general formula down at question 4 first. So from there we can probably sub in the value which we have extracted earlier for question 4, and we can construct this expression for Q4, question 4b. Okay, so let's write down the expression first. The expression is just equals to a sine omega t. Well, here it should be plus minus kx, because the plus minus here determines something very important. Okay, so let's move on. Substitute stuff inside. Let's go through from left to right. First thing is amplitude. You have amplitude which is here 3 cm. Copy it down 3 cm. Next thing is the sine. So if you just straight away copy down sine, it might be very dangerous. So what you should do is you should check the shape of the graph, whether it's really a sine graph or not. So a sine graph should look something like this. Is this the thing that you see here? Well, I don't really think so. What you are seeing here is not something that looks like what I'm drawing right now. What am I drawing right now? It's a sine graph. But what you see, it's a sine graph being flipped vertically. The positive stuff become negative, the negative stuff become positive. So seeing that, we can know that it's actually a negative sine graph actually. Negative sine graph should look something like this. Okay, so knowing that, we can avoid a silly mistake by writing a negative sign in front. It should be a negative sine graph. So very important to make sure the shape of the graph align with the trigonometric sign or cos that you use, and whether there's any negative or positive sign or not. Okay, so we follow up with the substitution of omega. Do you have omega? If you know, well, let's just find it then. Omega equals to 2 pi f. Then 2 pi times 50 hertz. Then it's just 100 pi radian per second. So method of substitution. Okay, you don't need to multiply the pi and make it a very complicated decimal. Usually when we want to construct an expression, you want to keep it clean. So write it in terms of pi is actually encouraged thing to do. When you are constructing an equation, if you are writing 100 pi radian per second, if you feel uncomfortable, do times the pi and write out the exact value. T The plus minus, I'll just leave it blank here because there's more to be discussed. Then we have k, which is just 2 pi, and x. Then you close the bracket. So what does the positive and negative sign in this space here represent? So what's the meaning? To know what's the significance of this positive and negative sign here to this expression for displacement, we use this online software called Desmos. It's a very powerful software. You can just Google it, Desmos, and with this software itself, you can plot or you can sketch very complicated graph just by writing down the equation in this corner here. Then the graph will just pop up by itself. Okay, so what I've written here, it's an expression of displacement, which is what you have written for question 4b, but I'm not sure whether I should put a plus or minus here. Okay, just to let you see, this is exactly the same as the equation I have now, except that I don't know whether it's positive or negative that I need to fit in here. So here, now I switch on this graph, then you can see this is my graph. It has an amplitude of 3 cm and it's a negative sine curve. It goes down from the equilibrium position, not goes up. If it goes up first, then it's sine curve, but now it's going down, negative sine. Okay, then you have omega t plus, we put the plus first, then kx. K here is 2 pi, therefore we know our lambda will be 2 pi divided by k, which is 2 pi divided by 2 pi. Then you have 1 cm as our wavelength. Okay, so everything fits. So what happens if I press play here is the graph will move. But now as you see, you might be very confused whether it's moving to the left or moving to the right. Everything is just so confusing. Why? It's because the omega here. The omega here is 100 pi, and you know the frequency is 2 pi f, means by it has a frequency of 50 hertz. 50 hertz is really fast for a wave that is really difficult to see using naked eye. So to illustrate this graph clearly, the motion of the graph, I will change this to just 1 pi to make the whole graph, the motion of the graph, easier to be seen. So let's see this whole thing again. Now you can see clearly that the graph is shifting to the left. The graph, you can think of it as moving to the left, it's propagating to the left when you put a positive sign here. Okay, now if I change this to a negative, then now you see if I put this as negative, then as time passes, this graph is moving to the right. So we can sort of make a simple conclusion that positive to the left, negative to the right. Okay, so this is just proving that positive is to the left, negative is to the right. Why is it possible that when you switch the sign, then the direction of the wave can change? You can think of changing the sign from positive to negative. You can think of it as flipping the x-axis horizontally. So you flip the negative x to become x. The x change to become negative x. You flip the x-axis horizontally. So before that, if things is moving to the left, now it will be moving to the right. Okay, that's a simpler way of explaining it. Okay, if you are curious whether this negative 3 here will change the direction, let's try it out. If we change this to just 3, then you see it's still moving to the right. If I change it to negative, it will still continue move to the right. So means by the sign in front of the amplitude doesn't change the direction of the propagation of the wave. So that's what this thing tries to say. Positive to the left, negative to the right. That's all. So we know from just now that if it's a positive sign, then it means by the wave is moving to the left. Positive, the wave moving to the left. If it's negative, the wave is moving to the right. So what direction is our wave moving? We have indicated it very clearly that it's moving to the right. And it's written here, moving to the right. So since it's moving to the right, the answer will be negative. So it's important for us to be really clear what's the direction of the motion of the wave. What's the direction of propagation of the wave before we fill in the positive or the negative sign. So there's a lot of sign to care about, whether there's sign here or not, and whether it's positive or negative sign here, or it's positive or negative sign here. Very important to consider, so be careful when you are constructing an expression of displacement as a function of x and t. So that's all for question 4. Thank you very much.